Hello guys, how's it going? Welcome to another video of tutorial series of building mathematical logic using PHP. Today, I want to get back to the prime number. I don't know, but I'm just in love with prime. I just love to research about prime. And maybe because of the fact that the prime is really random in its nature, and it's really hard to predict the prime when the number gets very large. But since we have already and developed some of the algorithms and some of the logic to print out prime numbers. But there are some more amazing facts about the prime number that helps us to identify primes in better and efficient way. So in previous examples we have seen, we saw that we generated primes using three different series. Like in the first series, we used the most basic approach of dividing a number, trying to divide a number with all of the smaller numbers and check to see if any of the number divides that number except for one. And if it does, then that is not a prime, and if it doesn't, then and that is prime. That was our first algorithm. In the second algorithm, we went to the half of the number because we know the smallest number that a number is divisible with is at least the half. For example, 100 is divisible by the largest number that can be divisible, that can divide 100 is 50. 51 can never divide 100. So we don't need to check for all of the smaller numbers, but we can start from the half of the way. That is, for 100 we check for starting from 50 and moving down to 2. So if any of the numbers between 50 and 2 divides 100, then that 100 is not a prime. But in case of, let's say, 37, we don't we can start checking from 18 or 19 and move till 1, and none of the numbers from 19 to 1 divides 37, so 37 should be a prime number. So we reduced the number of loops by half of the number. In the third, what we did was we divided the numbers only by the primes. We didn't check for all of the smaller numbers, but we check all of the smaller numbers that reaches till the half of the way of the number. So for example, we just check when we compare 9, when we want to check if the 9 is prime number, we don't check with all of the numbers starting from 8, 7, 6, 5, 4, 3, 2, 1, but we know that there are only two primes, that is 2 and 3, which is half of the way of 9. For example, the half of the 9 is 4.5. Let's call it 5. So there are only 2, 3, and 5 that we need to check the number with. So we just checked with all of the prime numbers, and that reduced our loop drastically. And today I want to decrease the loop more. So what I want to do is I want to copy all these, and I want to create another file called prime4.php. So this is our fourth video on prime. What happened? Into the puddle. Maybe I just created new file prime4.php. Prime4 already exists. Okay, so prime5. Okay, so we created a prime5, and let me just copy prime4 and paste it over here. So this was the one that we talked about. We just need to move to the halfway and just compare, just try to divide the number by smaller numbers that is only prime up till the halfway. That was what we did. And today, if you're confused about how we did this, you can refer to our previous videos on prime, 2 or 3 videos earlier. So you can just go and check to see if everything is good. But today we want to reduce the number of loops more and try to make our code more efficient. So let's just go back to see what we did in prime4. I just copied everything from prime4 to prime5. So let's check to see the number of loops in prime5. So we can see number of loop is 317 to print out all of the prime numbers from 1 to 100. Let's see if we can reduce this more. Okay, so let us try to visualize about prime number one more time using our recent. And today what we'll be discussing about, let us just write down some numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 11, 12, 13, 14, 15, 14 and 15 and 16 and 17 and 18 and 19 and 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, let's just discuss till this number. Let us just identify the multiple of 6. So we have 6, we have 12, we have 18, we have 24, and we have, let's make it one more, 30. So if we identify the multiple of 6, then we can see the prime number always lies in front or back of the 6. So 5 and 7 both are prime number except for 2 and 3. Let us just escape 2 and 3 because 2 and 3 are not in front or back of the prime number, but all other prime numbers except 2 and 3 lies in front or back or both of the multiple of 6. But it is not necessary that any number that is in front or back of the multiple of 6 is a prime number. But for a number to be prime, it should always be one less or one more than the multiple of 6. That is a rule for prime number. So if you see here, 5 is a prime number, 7 is a prime number because they both are one less or one more than multiple of 6. Similarly, if we try to find out another prime number, 11 and 13, both of these are one less and one more than the multiple of 12. Similarly, if we move towards 18, which is another multiple of 6, then 17 and 19 are one less and one more than the multiple of 6. But if we move to 24, 23 is a prime number, but 25 is not a prime number. So it is not always that prime number is one less or one more than the multiple of 6, but in general, all of the prime numbers is either like one less than the multiple of 6 or one more than the multiple of 6. Other number could also be one less or one more multiple of 6, but for a number to be prime, it should always be one less or one more than the multiple of 6. So our theorem states for a number to be prime, it should always be one less or one more than the multiple of 6, but that does not necessarily makes the number prime. So we cannot surely say that if a number is one less or one more than the multiple of 6, then it is a prime, but we can at least say that for a number to be a prime number, it should be one less or one more than the multiple of 6. So let's see if we use this theorem, or if we use this rule of mathematics, can we reduce our loop? So let's see. We are checking against I. We are checking for I against all of the numbers by trying to divide it. So before moving forward to divide it by all of the prime numbers, why don't we first check if I is one less or one more than the multiple of 6, and if it is not, we don't need to move ahead to divide it by all of the prime numbers. So because for a number to be prime, it should always be one less or one more than the multiple of 6. So I just want to introduce one new logic over here on the top of the loop, that if I plus 1 modulus of 6 is 0, or $I minus 1 modulus of 6 is equal to 0. Only in that case I want to move down, otherwise I don't want to move down. So instead of saying I is not equals to 0, and $I minus 1 modulus 6 is not equal. If both of these are not valid, then I just want to skip the loop. I don't want to check further. So for a number to be prime, I plus 1 modulus 6, either I plus 1 modulus 6 should be 0, or I minus 1 modulus 6 to be should be 0. And if both of them are not 0, then I don't want to continue the loop because the number cannot be prime. Because for a number to be prime, it should be one less or one more than the multiple of 6. So this is our stuff. So let us see if we can generate the same number of primes but reduce the loop. So we have 317 loops by just adding one condition that we just added. Let's see if we were able to reduce the loop and able to get the answer correctly. So we have 317 here. If I refresh, it reduced to 171, which is absolutely perfect. and the number of primes, we can see we just skip 2 and 3. I just want to remind you 2 and 3 should be skipped. But I think I made some mistake because even 5 is skipped over here. And the reason why 2, 3 and 5 is skipped is because of this, because 2, 3, 5 is not 1 less or 1 more than the multiple of 3, as we discussed earlier. Except for 2 and 3, this is valid for all of the things. So what I want to do here is I just want to skip for the case of 2 and 3. So which means only check this condition if I is greater than 3. So what I want to do, I just want to add one new condition over here, and or I is greater than 3. Now let's try to check if we get the proper values. So you can see we have found 3, 5, 7, and the reason 2 is not being printed is because we have just assigned 2 in the prime like this. So why don't I just echo $I and echo br over here, so that we just get 2, 3, 5. So previously, let's just check prime 4, maths.test prime 4.php. So we had 317 loops, but by just adding one condition over here, we got the exactly same result. But now we have 236 loops, which is quite less, almost 100 loops less. So as we keep on increasing the number and increasing the number range, like for example right now we are only trying to find the prime numbers between 1 and 100. So loop is 317 for previous approach and 236 for new approach. But if we try to find out the prime numbers between 1 and 1000, let's try to do that in both the cases. In prime 4, let us just make it let's just find the prime numbers from 1 to 1000, and in prime 5 also let's do the same thing and see the difference in the number of loops, and you might be amazed with that. So for our previous approach we have like 9741 loops, and in our new approach we have 8910 loops. So we have around 1000 loops lesser than our previous approach. And there are more approaches to enhance this series of code of printing out prime numbers, which I'll be dealing with in the future videos. And you see, once we crack out, I know it's really very hard to crack the perfect algorithm or most efficient algorithm to find out the next prime number. And you might be amazed to know that there are lots of supercomputers which is just responsible for finding out the next prime number. And we have books in big volumes, and that only contains the prime numbers. And you can see that some of the numbers goes up to like 100 digits and 1000 digits, and one whole book full of one digit, one number with thousands and thousands and millions of digits, and which is identified to be prime. So just imagine if you want to find out the prime number with greater, and let's say the next prime number, which could be in millions of digits in number, and in that case we really need a very efficient code to find out, to preserve, or to secure our resources, to use the least resource and find out the prime numbers. So these are the steps that help us to write the code so that the number of loops and the number of processes is drastically reduced, so that we can someday have a good and best code that will determine if the number is prime or not. So there are more concepts like, we have a series called Lucas series, and Lucas series also helps us a lot to find out if the prime number is prime or not. So which we'll be dealing in upcoming videos. But for now, this was one of the most important theorem that helped us identify if the number is prime or not. So I hope you like the video. Let me just switch this video back to 100, 1 to 100. I just don't want to modify my codes. So this is one more video regarding the prime number. I hope you like the video. I'll just push these videos in my Git repository, and I have shared the Git repository with you in every videos. You can find the link to my Git repository in the description and my Facebook page in the description. So don't forget to like and subscribe to the video, and if you think that this video was really interesting and useful, don't forget to share it with your friends. I'll see you guys in the next video. Till then, have fun. Thank you.